DNS traffic today. But first, who am I? I'm a researcher at OpenDNS, and the majority of my work is on pattern recognition for signals intelligence. So what's going to be kind of the main focus of today's talk? It's going to be about how can we model DNS traffic and what type of information can we mine from DNS traffic. And the last part of the talk is then going to be focusing on a variety of techniques that allow us to accomplish these goals. So you can think of the talk being broken up into 3 sections. The first is going to be kind of the motivation behind what made the team decide to pursue these problems. The second is going to be a set of methods where I will be discussing a spike algorithm as well as a clustering algorithm. And then finally, we're going to have a brief discussion of some of the results that we've obtained. So first of all, what exactly is DNS? If you want to do traffic analysis, we need to have a pretty clear understanding of what DNS is. Many people liken it to the internet's phone book because it helps us create a mapping relationship between domain names, which are easy for humans to understand, and IP addresses, which are really easy for machines to understand. And so, of course, you can imagine that remembering a 32-bit number is hard for a human, but easy for a machine. DNS helps fix this issue. So we can think of then DNS as being set up into a variety of zones, as this diagram over there neatly shows. And so when you have a question to say go to google.com, you send out your request, and your request goes to the .com zone. The .com zone then has its information about the underlying subtrees and then sends another request to the Google zone. So eventually, in order to get an answer, your question must traverse the entire DNS zone area for your path. And once you receive the answer, it's cached in your browser. So there are now 2 types of DNS services, and this is actually quite important. There's an authoritative service and a recursive service. Authoritative services you can think of as the actual phone book itself. There would be, for example, a server that's in charge of maintaining all the information for the .com zone. However, when you're a normal user, you actually interact with the recursive server. The recursive server is the server that's doing all the question and answering for you. So where does OpenDNS fit in this picture? Well, we are a recursive server. We currently have 2 IPs where you can point your DNS server browser to, and we will then basically send you a set of answers back for any domain question that you have. So we have 24 resolvers worldwide. We use Anycast, which is actually important, as we'll get to later on. And we see about 50 billion queries a day, which comes out to about 12 terabytes uncompressed. So it's a pretty large data size. But at OpenDNS, there's 2 types of data that we collect. There's what's called passive DNS, and then what we call recursive DNS. So this distinction is important when it comes to modeling some of the traffic patterns that we're going to be talking about later. Passive DNS just maintains a historical mapping between a domain to an IP. So that means with a passive DNS system, I can see 10 years ago what google.com was mapping to. It gives us a very good understanding of how domains and IPs have been changing over a period of time. However, we're not going to be talking about passive DNS today. A lot of work has already been done on passive DNS by professors at Georgia Tech and Damballa and OpenDNS. Passive DNS is really good for certain types of data analytics. However, it's not the greatest when you're trying to catch specific types of threats. And that brings us to the fundamental question. What are we trying to model? And more importantly, what can your data actually model? Whenever you're attempting to use some sort of data algorithmic method, the most important thing is determining the quality of your data and figuring out whether your data has enough information to actually make the type of inferences you wish to make in order for you to create some sort of classification system or pattern recognition system. So CrimeBear is, I like to think of CrimeBear as an ecosystem. You have like your botnets, your exploit kits, your spammers, and it's constantly evolving. And passive DNS is great for catching fast flux servers and DGAs because they make a lot of noise in the authoritative zones. A DGA creates a lot of NX domains which are easily noticeable, And fast flux domains are constantly changing their name servers or their domain to IP mappings. So we have a set of really the community has created a set of techniques to really easily use passive DNS to capture these types of threats. And as a result, if you're a network security operator at any large corporation, you have a blacklist, which is many times fed by using and mining data from the passive DNS. And the best method that's currently used is this idea of reputation. That is, a certain domain or an IP might have some sort of historical reputation, i.e., I might know that domain X has a history of hosting Russian spammers. And as a result, when I see outbound or inbound traffic coming from such a domain or IP, I want to block it. So people have come up with a set of techniques using passive DNS and some magic to give us the answers to these blacklist questions. The problem is, this was great in the early 2000s. Getting IP space is cheap, domains are cheaper, and subdomains are the cheapest. So what this means is, if you're an attacker, you can easily buy a little bit of IP space from a VPS provider, host whatever malicious content you want to do, and then quickly tear down the service in a matter of hours. Passive DNS is too slow and many times does not record these type of transactions correctly because you don't get to see the actual flow of new IPs being created unless you get an entire global reach, which no individual or company has. Furthermore, compromised domains are a new threat. A compromised domain is when you have a totally benign website that has some sort of flaw that can be exploited. This is a great way to get around IP reputation or domain reputation issues because you would expect that a benign website that has a very clean history will not be hosting a ZBot dropper. However, many malware authors have found a variety of techniques to find compromised domains. So passive DNS isn't good at catching these types of threats. So what's coming? Exploit kits. Exploit kits are the primary source of botnet and spam infections in the crimeware ecosystem. So if we could figure out a way to model their behavior, you would have a very good method of identifying how attackers are moving throughout the IP and domain landscape. Furthermore, exploit kits use a large distributed network, not unlike a content delivery network. As you can see by this diagram, the majority of droppers and botnets that you're familiar with are using exploit kits as the initial vector. So this is a classic kind of example of how the exploit kit flow goes. You have a bunch of poor guys who visit a set of websites, and these websites redirect them to a set of malware distribution servers. These servers then send them through further redirections until finally they reach what's called the dropper page. And this can include a variety of domains along the way, rotators, routers, and then finally dropper pages. So what I want to focus on is exploit kits, because I think understanding how exploit kits work give us a very good way of understanding how botnets will evolve and how botnets will also emerge in the future. Because in order for a botnet to even infect users, it needs to use an exploit kit to exploit the user first and put the botnet software on that user's machine. So let's start with a very simple idea. Exploit kits have a set of domains that are all connected in a chain. You might expect a user to click on perhaps one of those domains on purpose, but not the entire set. This gives us an interesting idea. How about we have the following hypothesis? DNS query patterns can help us identify domains hosting exploit kits. Not passive DNS patterns, but instead recursive DNS patterns. That is, we can look at how clients are interacting and sending out requests to a set of domains, and then from that information, be able to mine significant patterns out of that signal that can be associated with exploit kits. Then we can use passive DNS to help us catch even more exploit kits, because we know that exploit kits like to reuse large infrastructure. But in order to gather the seeds, we have no method of using passive DNS to find the initial exploit kit domains themselves. And that's why we want to use recursive DNS data to help us catch these new domains. So right here is a traffic pattern of 2 exploit kits that came up in, I guess, mid-February. As you can see, for about the previous 2 weeks, there's absolutely no traffic. And then suddenly, in a matter of 1 to 2 hours, there's a large spike. And this kind of makes some sense, because if you're an exploit kit operator, you don't want a long-lasting service at a domain. You want your domains to be easily put up and then easily put down, so you don't get the authorities on your back. Furthermore, you don't want to register an exploit kit domain for a very long period of time, because that's going to cost you money. So what many exploit kit authors like to do is to do some form of domain tasting for just a matter of days and then dispose of their domain. This means that exploit kits are disposable, cheap, and very short-lived. So really, we're looking for a spike-like pattern within the DNS query pattern. Because as you can see, on February 17th, at around 12, a set of users suddenly put out a host of DNS queries to an exploit kit domain. So with this idea, let's form a very basic algorithm to help us extract spikes from domains. Let's take 2 consecutive hours of recursive DNS traffic. Recursive DNS traffic contains information regarding a timestamp, the client IP that is requesting the DNS the DNS domain, and the domain name itself, and a set of R codes and Q codes. You first want to then count the number of queries received per domain per hour slice. We then perform a join where the key is the domain, and that allows us to see the domains that have been spiking in hour 1 and in hour 2. We then finally filter out any domains that have been receiving an abnormally large amount of traffic. So that would be like your Googles, your Facebooks, and your various content delivery networks. And so then this then leaves us with a set of domains that have had some sort of rapid increase in DNS query patterns in the last 2 hours. So at this point, you kind of think to yourself, well, we're done. We've created the algorithm. There's nothing else to do. All we need to do is run it on a couple hours worth of data. We'll probably receive a set of spiking domains. And those spiking domains we can easily push to the blacklist. Unfortunately, all we see is a ton of noise. There are a ton of domains that spike in consecutive hours. To put this in perspective, 1 hour of traffic is about half a terabyte of data. Once we perform this spike algorithm on 2 consecutive hours of traffic, we see about 20,000 domains that have been spiking in that period. That's too many domains for a human analyst to go through, and probably far too many for a very naive heuristic method to filter out. So we need some new techniques to help us out here. So for example, this is a spiking domain, which you might think is actually malicious, but in fact, it's just an example of a DNS amplification attack. So we can't actually block this website because it's a totally benign website. It's some poor person who, I guess, misconfigured their DNS server, and somebody is exploiting it. But we can't actually put that on the blacklist because it's not a true malicious website. So we have to be very careful when it comes to kind of deciding what we can consider malicious and what we cannot. And that then brings us to a much larger problem. A lot of people, and in recent years, there's been a lot of kind of talk about machine learning and bringing big data and data science to the field of security. One of the hardest things to establish is this idea of ground truth. Ground truth is the idea that when you're given a set of domains, you have or a set of objects, you have a very clear understanding of what those objects are. Because for any type of classification system to work, you need to be able to kind of say with certainty that an object is an apple and an orange. The challenge here is we have very little idea of what these domains are initially. We have about 20,000 domains, and we can't manually inspect them to classify them. So we want to use a technique from the machine learning community called unsupervised learning. It's not going to be classifying anything for us. Instead, unsupervised learning is a set of techniques that allows us to explore the data by analyzing essentially the shape of the data itself. So we can use unsupervised learning as essentially a pre-step before we create our actual classifier. So the goal really, for the last couple of months, has been to create a set of algorithms that allows an analyst to analyze a set of spikes and then determine perhaps what kind of groups of spikes emerge in the data. So the method that we decided to use was clustering. Clustering, as you can imagine, just helps us find similar groups. And I decided to use the most basic of clustering algorithms, k-means. You can think of k-means boiling down to just kind of this little function right here. You don't actually need to really kind of focus on the math. The idea behind k-means is the following. We have a set of points. And these set of points, we believe, belong to a set of groups. What we want to do is create the ideal sets where if we go to every single point in a set, we can say that its average is minimized. Basically, if I'm at point A in set A, and I go to point B, which is in set A, I notice that the difference between these 2 points is very, very small. And if you do this for a set of points, eventually what you find are these things called centroids, which are kind of the center of n-dimensional objects. And so with k-means, then we have to solve this summation of a set of means. The technicalities aren't that important, but this function becomes quite important later on when it comes to kind of choosing the number of clusters we imagine to be in the data. So as you can see, at step A, we have a set of data points. And we iteratively go through each step, and we kind of create naive clusters. We make kind of guesses on how big the cluster is and how many points are within the cluster. And at each step, we keep adding points to the cluster, or we remove them. And this continues for a set of iterations. So it doesn't run once. We have to run it multiple times. And we also have to basically choose where we start at random at each time, because you don't want to start at the same place every time you run the algorithm. And because we're trying to minimize the mean, or kind of the average variance within a set of points, we're essentially acting as a least squares estimator for people who are familiar with any form of regression model. This causes some problems, however, with the type of data that we're working with. Okay, so she just asked, how do we choose a number of clusters? We'll come to that problem in, I think, 2-3 slides, so don't worry. Okay, so now we have an algorithm that we want to use. Then it just becomes choose a set of features, we scale them, and we run the algorithm, and we're done. Unfortunately, it's not that easy. One of the most complex parts of this entire pipeline is actually choosing the features, because the features are what determine kind of what should be examined, what should be considered as something that's important to look at when creating a cluster. So we chose the following set of features: the number of query counts, the number of unique IPs, a resolver distribution, and the R code distribution. And what we then did was filtered out all domains that had less than 3 unique IPs. Now, at this point, you might be thinking, well, this isn't that many features. Why would you kind of just stop at 4 or 5? Well, the reason is there's this problem of in kind of machine learning called the curse of dimensionality. And as you increase the number of features to kind of help you create clusters, you also then kind of make everything look the same. So essentially the problem is, let's say I added 100 features to kind of determine whether something's a spike. The more features I add, the more similar any 2 points start to look in a high dimensional space. And so one of the biggest goals is trying to choose as few of features as possible in order to kind of minimize the amount of unnecessary calculations that you're doing, and possibly creating incorrect clusters within your data set. So we now build an n by n matrix to kind of store our samples and our features. And n is the number of samples. So that's every domain is considered a sample. And M then is the number of features. So we have our M, we have like, in this case, 7 features. And so we have a 6,000 by 7 matrix that we're working with. So if any of you have been working with k-means in the past and kind of been listening to what I've been talking about, you notice that I'm doing some hand waving right here. And that's because I'm dealing with query counts. And query counts are discrete data points. So for example, I can expect to see in an hour 5 DNS queries or 10 DNS queries, but I actually will never see, say, 10.5 or 6.5. So this doesn't seem like that big of an issue. However, the problem is a lot of the techniques and tools we've been using make some very strong statistical assumptions on the actual underlying distribution. So k-means operates on a normal distribution. And the normal distribution is kind of the familiar Gaussian that we all see in school, or have seen, I guess, in images. And a Gaussian distribution expects continuous data. That means I would expect to see 10.5 queries an hour, 11.5 queries an hour, but the data that we're working with does not follow this normal distribution. If anything, it follows what's called a Poisson or a negative binomial distribution. So I had 2 options at this point. I could either kind of rework the algorithm using the Poisson distribution or some sort of other distribution, or I could kind of just charge ahead. I decided to charge ahead because rewiring this stuff for these 2 distributions would become a lot of work, and I wanted to first see whether there was enough error in using a normal distribution before I decided to just completely toss it away. So that's kind of the caveat, and something that's really important whenever you're working with data is to know kind of what type of data you're working with. In many times, you might think that you have a fantastic algorithm, but if your data is, say, categorical data, where you're just measuring, say, the number of boys, girls, doctors, or count data, your algorithm is not meant to basically handle that type of input. And so one of the key kind of challenges is figuring out how to either massage the data to make it more acceptable for your algorithm, or just choose a completely different algorithm. And so finally, what we do is for each feature, we calculate its mean, and we remove the mean, so that means that we essentially scale it to 0, and then we divide by the standard deviation. That's kind of the normal whitening approach. And this works really well with k-means because k-means is an algorithm that is aimed to essentially identify various signal properties quite well. So it's almost expecting some sort of wave or spike when it's clustering. So we kind of made these assumptions, and we went ahead. So now comes the question of how do we choose the number of clusters? Many times, software libraries will kind of give you an initial cluster count. I believe sklearn gives you 8 as the initial. But in this case, we have a very kind of crude technique to help us estimate the number of clusters that exist in the data. So if you remember, we had this equation over there, and we call this the distortion function. The distortion function basically told us kind of how much movement is going on, how much variance is going on every time you run this algorithm. So it's a good way of kind of figuring out how much change overall is happening every time we add clusters or remove clusters. So with that kind of understanding, we can kind of come up with the following idea. Let's assume that we can have between 5 and 20 clusters. And now let's start mapping out what the distortion function value is whenever I do a k-means algorithm for that number of clusters. And then let's just see what it looks like. So this is what we get. So as you can see, when we start off at 5, we have a pretty high level of distortion, and then we keep going down. And it looks something like an elbow. And so this method is called the elbow method. Basically, you're looking for kind of the crook in the elbow, and then you want to move a little bit past it. A little bit past it is subjective, but the best way to kind of determine how to choose a little way past it is to actually look at the cluster sizes eventually. And so we have this algorithm, and so what's kind of the underlying theory behind it? Well, the idea is, if I look between 5 and say 9, there's a really big drop-off in kind of in the amount of change that's going on when I increase the number of clusters. That means each new cluster that I add is giving me a lot more information about the underlying structure of the data. However, as I move further on, say between 15 and 20, the rate of change and distortion is a lot slower. This means that adding additional clusters doesn't give me that much new information. And if anything, I'm basically wasting computational time as well as creating false clusters. So what I really want to do is kind of find this sweet spot within the curve. It's kind of like, I guess, find like the inflection point within this curve. So this is kind of what happened when we ran the various set of clusters for 10, 11, and 12. And so as you can see, the cluster sizes begin to drop off quite dramatically. And as a result, I ended up just kind of choosing 12. I kind of went between 11 and 12. What's interesting to note is how there are a couple of clusters that are extremely small. Cluster 11 in k equals 12, cluster 10 in k equals 11. And this is actually a worrisome point, because the fact that you're generating such small clusters is a sign that there's some sort of very wide spread in your data. And k-means is not capturing that spread correctly. So this is kind of like a point to remember, and something that should be refined in further kind of improvements. However, this is still pretty good, and we can actually derive some pretty interesting observations from this. So the next question that you kind of want to ask is, how much does each feature help me kind of create my cluster, right? And this is important because if I have, say, a ton of features, we talked about this problem of dimensionality. So we really want to know that we're getting the most bang for our buck whenever we choose a feature. So we can then think about this as the following problem. Each sample or domain lives in what we call an n-dimensional space. And this n-dimensional space is created by essentially the number of features. So we can then think, as this diagram shows, if we map all of our, if you're dealing with only 3 features, we end up with a 3-dimensional space, and we end up with some sort of cloud of data points. Now, if I'm dealing with only 2 or 3 dimensions, this becomes quite easy to determine what features contribute the most to the clustering, because visually it's quite easy. However, we're dealing with, say, 6 or 7, and that's kind of hard for your eyes to understand. So the question is there an analytical method? And thankfully, there is. So the there's this technique called principal component analysis, and we don't need to go over the actual details, but the general idea is we assume that our data is some sort of cloud, right? And we know that the most important features are going to basically create the most stretch in the data, because they're kind of what's drawing the data towards them. So with that in mind, we want to create a set of techniques that can essentially find the most important directions within the data. So this can be solved as a linear algebra problem where we think of the data as a giant matrix. And what we're looking for is this idea of the covariance matrix of the data. Covariance refers to essentially the change in standard deviation per each dimension. So once we have this covariance matrix of kind of all these data points, we want to find which direction is it changing the most in. So then we just calculate the eigenvalues and eigenvectors, because eigenvalues and eigenvectors give you the directions of your data cloud, and the eigenvalues tell you how important each direction is to the overall change. So I create a covariance matrix, I calculate its eigenvalues and its eigenvectors, and then I find the largest eigenvalues and its corresponding eigenvectors, and I look at them. And then I get the following values. Essentially, query counts accounts for around 33% of kind of the information within my data. And by information, I mean like it's probably one of the most important kind of variables used to kind of create my clusters. I'm only showing you 3 instead of the entire 7, just for kind of space. After you can come and talk to me about that. Unique users is around 20, and unique resolvers is around 13%. The problem is we want to do better. So there's one last feature that I decided to add in. So I talked about how we were only looking at a 2-hour window. And so the problem is there's all this stuff that's going on before, right? So let's say that between hours 12 and 1, a domain is spiking, and then 5 hours previously, it had a little bit of traffic, but it wasn't really spiking. That information in the first feature set that I talked about would not be captured. We don't really know kind of the previous history of the domain. But that's really important because we know that exploit kits in general go from 0 to 100 really quick. As a result, we want to kind of measure some sort of measurement for kind of the volatility of the past query traffic to the domain. And the method that we decide to use is this idea called the Fano Factor. And so in statistics, the Fano Factor is this idea of dispersion. Essentially, we take kind of the standard deviation, that's kind of the spread of queries over some time window, and then we divide it by the mean. And that kind of gives us some sort of dispersion index. So when you're dealing with, say, dispersion that is very close to 0, that means that you're dealing with some sort of distribution that's going to have extremely abrupt changes. Excuse me, dispersions that are greater than 1 usually means that there's a high degree of change and variation within that query pattern. And so this is very useful as a method to help kind of identify domains that have had a long history and have some sort of potentially spike-esque like pattern to them in the past. So now we can talk about some of the results that we had. So we had about 12 clusters, and some of the interesting kind of clusters that emerged were mail servers. Mail servers love to spike at very kind of predetermined hours of the day. We caught about 1,000 mail servers, which kind of go from 0 to around 200 about every hour. These are completely benign mail servers, so it's just kind of normal query patterns. What's more interesting, however, is some of the DDoS and spam that we see. So what happens is some attacker notices that somebody's kind of misconfigured their DNS, their DNS information. And what they like to do is they like to send a ton of DNS 255 requests, which are DNS any requests. And as a result, you get this huge packet back. But they're spoofing their IP, right? And so essentially some poor unsuspecting person gets giant DNS responses from a set of domains, and they get kind of overwhelmed with traffic. So DDoS and spam is a very kind of common technique and cluster pattern that we saw. And one interesting thing about DDoS is that for most exploit kits, you see very kind of low frequency query spikes. So you're going from, say, 0 to maybe 200. DDoS goes from, say, 0 to 3,000. They're much higher in height. And that kind of makes sense because they're essentially trying to get as many kind of DNS responses as possible within an hour. We also noticed something similar to DDoS in our attacks on WordPress sites. People would try to brute force WordPress sites, we believe, by trying to kind of just do password brute forcing. And this was kind of verified by looking at some of their IPs and some previous history. And then we also saw a lot of kind of bizarre clusters like Tumblr. A lot of Tumblr websites would spike and then kind of go down to nothing. The bottom 2 spikes right there refer to Tumblr domains. And as you can see, they're almost identical. So there's some group of people who every couple hours decide to visit Tumblr en masse. And finally, then there's the most interesting part, the exploit kits. So we were able to kind of successfully find quite a few interesting exploit kits within all the junk in one of the largest clusters. So exploit kits were grouped quite well together. And one of the most interesting cases that we found were actually a lot of compromised domains. So we found this website hosted on I guess it belonging to some Turkish user called Escort La Bursa. And it had the following subdomains spike up, as you can see. And now our guess is that escort La Bursa was compromised, and these subdomains were actually injected. So is anybody here familiar with like domain shadowing? I know Cisco put out a report, and Dia Majoub has talked about it in the past. It's this idea where people are able to kind of hack registrars based on some sort of vulnerability and then inject subdomains into various websites. And so for the longest time, people had been noticing that GoDaddy was the biggest kind of contributor to this whole domain shadowing problem. And what we started to realize is that there's actually quite a few other registrars that are also fallen victim to this. So all this work had to be done manually, but it could not have been possible if we didn't kind of have easy methods to kind of separate the data. So with this new domain, we then used escort La Bursa as a seed and then kind of leveraged all of our passive DNS data to help us find new malicious domains. And so as a result, we actually ended up finding an entire IP space that was used by these guys to host some pretty bad stuff, and you're able to block it all out. And so actually that's about it. I'd like to thank Dia Majoub. She's a senior security researcher at OpenDNS. It's a lot of the advice he gave me. And of course, the rest of the team at OpenDNS and John Lamping. Okay. Are there any questions or? Hi. Yeah. Sure. Oh, sorry.
Two questions. The first is, why you do assume that a Gaussian distribution wasn't good enough? And why I didn't understand why you didn't use a Poisson distribution. And the second one, do you guys try any case of supervised learning to maybe classify first and then analyze this before doing a supervised?
So I'll answer your second question first. With supervised learning, you need to have a pretty good understanding of everything that you might potentially see. And when we first kind of started this project, we didn't have that good of an understanding, essentially the ground truth. So we wanted to use unsupervised learning as a method first to kind of understand what's going on. And once we get that baseline, we can use more supervised learning techniques. So we're starting to kind of come up with some supervised learning techniques for this type of spike classification. As for your second point, it really kind of like, if I understand correctly, it's like, why did we use the Gaussian? Yeah, so, we didn't want to use, we didn't want to use a Gaussian because for count data, where everything is greater than 0, Gaussian distributions don't work as well just because of scaling issues. Using a binomial distribution would be ideal, some sort of negative binomial. I was just kind of lazy. I didn't want to code up an entire, it's a pain, it's a little bit of a hassle. So see what's quicker.
Yep. Are you seeing any evidence of long TTLs to minimize DNS spikes or pre-warming of resolver caches? Are you seeing long-lived TTLs to reduce the spikes and any pre-warming of resolver caches?
So actually, we're not looking at any of the TTL data when we're doing the spikes. So that would be probably one of the techniques that we want to start using when we already have nice clusters as an additional layer of clustering. So there, as you notice, there was no lexical analysis done. There was no kind of analysis of TTLs. I just wanted to purely look at the actual signal pattern itself. Because the more features that I was adding in, I was concerned that it would really kind of distort kind of how the algorithm would kind of process the data, especially if I'm dealing with TTL data, which follows a completely different distribution than, say, query pattern distribution. So it was a trade-off. But yeah, absolutely. Using TTLs is something that will be done as a filter. Yeah. Yeah. Any more?